Okay, welcome. I'm going to hand you straight over to our host, Dr. Clara Barker, who is manager of the Centre for Applied Superconductivity in the Materials Department of Oxford University.
Hi everyone, how are you doing? So thanks everyone so much for joining us for this talk. So this is the second in a series of talks which are being put on by the Tigers in STEM, the Inclusion Group for Equity and Research in STEM. And so we've got two fantastic speakers joining us today, which is really exciting. But before we do, a little bit of housekeeping. So we do have a code of conduct. So hopefully on screen you can see a QR code, which will link you to the code of conduct. So it would be great if you could just have a look at that and make sure that you're compliant, because we do want to have a really good active chat in the YouTube chat, but we just want to make sure that everyone feels welcome and accepted here as well. Can we also ask that people do not record or take screen grabs? So some of the information that is being shared is not published yet, and so we're going to make sure that we deal with that before we put the video on YouTube later. So just be aware that this is people's data, so if we could not take screen grabs, that'd be great. We will try and run PowerPoint with captions. We realize that captions are not perfect, but we will run with captions. Sadly, I cannot run with captions on this version of PowerPoint for some reason, and so I apologize for that. I will say that this series is in memory of the late Claudia Alexander. So it's been run in memory of the late Canadian-American geophysicist and planetary scientist Claudia Alexander, whose work and leadership paved the way for many of NASA's missions, including the Galileo mission. As a Black woman who reached the very top of her disciplines in physics, a teacher and an author, she was a great role model and has left behind a legacy which inspires many, particularly women of colour working in STEM. In celebration of her contributions to science and recognition of the immense work that still needs to be done to support the next generation of STEM leaders in the UK, we are requesting that attendees of the webinar consider, if you're able, making a donation to the charity Generating Genius. This is a London-based charity which helps school students from disadvantaged backgrounds, particularly Black and BME, to enter university and enterprise careers in STEM. So there will be a link in the chat, and so it would be fantastic if you could donate, but like I say, if you can't, that's fine. For questions, do also use the chat thread. A little disclaimer, I believe that the Generating Genius webpage is just undergoing a little bit of maintenance, so you might not be able to do that right in a second, but I believe there is a link which we can make you aware of. So I don't want to take up too much more of your time, because we're not here to listen to me, we're here to listen to our two fantastic speakers, Idris, Ajia and Kate Oliver. So I'm going to introduce Idris first. So Dr. Idris Ajia, their talk is Gigahertz optical mechanical resonance in dielectric metasurface arrays. So Idris was born in Nigeria, but spent his formative years attending primary and secondary school in different parts of the country until ending up in the Republic of Benin, where they completed high school in 2005. Afterwards, Idris moved to Kenya, taking a foundation year course that allowed him to pursue an undergraduate study in electrical engineering and electronics at the University of Liverpool. After graduating in 2009, Idris proceeded to pursue a master's degree in engineering at the King Abdullah University of Science and Technology, KAUST, in Saudi Arabia. There he specialised in optical spectroscopy and received his degree in 2010. Following a master's programme, Idris did 1 year national service in Nigeria, after which he returned to KAUST in 2012 to pursue a PhD in material science and engineering. Idris spent the next 6 years investigating the ultra-fast carrier dynamics properties of nitride-based materials, nitride-based materials. In January of 2019, Idris joined the integrated nanophotonics group of Professor Muskens at the University of Southampton, where he is presently using ultrafast transient analysis techniques to investigate and characterize nanophotonic materials. Idris is the recipient of a number of awards and scholarships, including the University of Liverpool Attainment Scholarship Award, Cowes Discovery Scholar Award, Cowes Provost Award, and Cowes PhD Fellowship. And with that, I will stop sharing my screen and ask Idris if you could please share your screen. Thank you.
Great,
Go ahead. Thank you, Idris.
Hi, everyone. My name is Idris Ajia. Thank you so much, Clara, for the amazing introduction. I really do appreciate that. There's going to be a lot I have to say about gigahertz optomechanical resonances in dielectric metasurface arrays. So I'm just going to get to it without taking much time. But before I do, I'd just like to say a big thank you to the Tiger in STEM team for the phenomenal support generally, and just for putting this talk together. It's very much deeply appreciated. I'd also like to thank members of the Integrated Nanophotonics Group in University of Southampton, also for just being great team members and people to work with. So if you're listening, thank you, all of you. Now, this work is a collaborative effort between the Integrated Nanophotonics Group in Physics and Astronomy at the department at Southampton, and the Optoelectronics Research Center in the Zeppler Institute for Photonics and Nanoelectronics in Southampton as well. So the outline of my talk is quite simple. I will just run through metamaterials, starting with a bit of a general discussion, and then a little bit more about what I'm working on, and then I'll discuss the technique that I've used to investigate my materials, and then maybe get a little bit more specific. So there is a little bit of general and specific for, to make everyone happy. Before I go on, maybe it's useful to discuss, the whole point of metamaterials in particular. And I would just say this: it's photonics. It is basically the child of photonics, and it was birthed from since 1960, in the 1960s, I think, when lasers and optical fibers were first invented, and the idea of how then to transition from electronic devices to photonic devices came up, and the appeal of this proposition is evident when you look at the speed of photons and how much you can modulate photon. Just taking a single photon, for example, there's so much information you can store in it, like by changing properties like the polarization or the wavelength. And this is vastly different from electrons, where there isn't that much that you can change. And so in addition to all of these advantages that metamaterials, photonics would bring, metamaterials added a few more things, spiced it up a little bit more by telling us that there's so much more you can do. You could achieve negative index materials, which I'll go over in a bit, and also cheaply and passively you can manipulate electromagnetic signals, which also I'll go over. So what are metamaterials? I think perhaps the best way to start is to first understand what materials are. And just as a bit of a disclaimer here, I know metamaterials is a very broad field. So when I speak about metamaterials in this talk, just assume that I'm talking about photonic metamaterials that are used for optical reasons. So when you think about optical materials, right, you think about a periodically ordered cluster of electronically coupled atoms with optical properties that are dependent both on the elementary content of your optical material, as well as the way in which they're ordered. So in the same sense, metamaterial harnesses the same idea. So you basically have some some sort of element or meta atom, and these meta atoms are ordered periodically, just as you'd have in normal materials. Nevertheless, what distinguishes metamaterials from normal materials is that these meta atoms are so flexible that you can change their properties, which you can't easily do with elements. So this flexibility allows us to do all sorts of interesting things with the materials that then gives us the possibility to create unnatural emergent properties. So for example, one of the applications is in the creation of negative index materials. And to understand how this works, first we need to understand what the refractive index of materials is, right? And so the refractive index is basically a property that determines just how fast light would travel within a material, and it's you can further break it down into its components of permittivity and permeability. Now, under normal circumstances, transparent materials always have positive refractive index, and in most cases greater than 1 as well. And so this means that light would transmit through the material, but would be slightly slower, and that usually causes it to bend. We also have, on the other hand, opaque materials, which have negative permittivity, that are naturally occurring, like metals. And the reason that they're opaque is because they do not allow light to pass through them as a result of this negative permittivity. Now, on the other hand, we have another group of opaque materials that are not so common in nature, and this is where things start to get interesting, because what is negative about them is not really their permittivity, but their permeability, which is the way the magnetic component of electromagnetic signals interact with them. And I think it was Pendry in 2000 who first demonstrated a way to make negative permeability materials by using the split ring resonator design. And what this is essentially is that you have electromagnetic signal incident on your split ring resonator, which is made of some sort of metallic concentric metallic ring that is split. And so because the magnetic signal is passing through it, it induces some sort of electric current that goes around, and then when it encounters the split behaves as a capacitor. And while I acknowledge the nastiness of the equation of this, what you just need to know is that the interaction between the capacitive and the inductive property of this material creates some sort of resonance response. And in addition to that, because there is some sort of magnetic field interaction, at some point you're going to get a point where you'd have a resonance, but in the negative permeability region, which is a bit like you shaking a pendulum at the middle of the string that holds it faster than the resonance of the pendulum itself. So that would cause your shaking to go in the opposite direction of the pendulum. And now if you mix this property of the split ring resonator with the property of the negative permittivity materials, which we previously talked, that are arranged in some sort of lattice format, then you can have this interesting device where you can then have a overlap between the negative permeability and permittivity to create a negative index material. And the way to think about it in application wise is, say in your normal materials, when light is incident on them, if assuming the refractive index of the media through which the light is going through is greater than 1, then you'd have the light bend a bit towards the normal, right? Which is what you'd normally expect. And this generally respects Snell's law, So if you think about a negative index material, you'd have more or less the same, except that the light would bend in a way that mirrors a normal material with respect to the normal. And if you don't believe it, just perform a little mathematical trick with the trig relationship here, and you'd see that it works out. And what that translates to physically is that the phase velocity, or that is the velocity of the photon itself, would be going in the opposite direction of the energy of the photon. And this can lead to some pretty interesting phenomena, like super lenses, where you're focusing on an image or an object. You have two focus planes simply because of the way the light bends. Another interesting application of metamaterials could be optomechanical metasurface arrays and their use in the modulation of light. So these are materials that, when light is incident on them, the operating principle is basically that some other wavelength of light can then mechanically actuate some nanostructure, because that nanostructure is within or smaller than the wavelength of light that is incident on it. And because of that interaction, it can block the transmission of a different light. And there are many ways through which this can happen. So for example, you could arrange materials in such a way that two different thermal expansion properties are overlaid on each other, so that when light is incident on one of them and hits them up, the rate of expansion of one is different, and so it causes one of the strands where you have this overlaying configuration to bend. On the other hand, you have other strands that are sandwiched between between two different materials, one of which is on both sides, like a metal and insulator and metal, for example. So because of the cancelling out of the thermal effect, you don't have bending, and so you can create this sort of phenomenon. Another way you could do that is by having some sort of also nanostructure on your metamaterial that interacts with, say, radiative pressure, or the electric, or through the creation of electric or magnetic dipoles, to sort of create a repelling or attracting effect. The methods that I'm using in my own research is the use of dielectric materials, and here the reason is because you don't need any sort of complicated configuration. All you just need to do is etch out some parts, and then you essentially have some sort of nano cantilever effect. And what we're leveraging here is the physical properties of these materials, like the stiffness and all that. So as the nanostructure gets smaller and smaller, it gets to a point where the radiative pressure that's incident on that nanostructure becomes comparable with the elastic force of the structure, and then this creates some sort of resonance or oscillation on the surface of the material. So this was demonstrated earlier on by Bruce in the optical, at the Zeppler Institute. So nevertheless, this structure had some limitations on the speed of the oscillation, which was within a couple of megahertz, due to the low stiffness, or Young's modulus, if you like. So in my experimental structure, what I'm leveraging here is, sorry, it's a bit slow. So what I'm leveraging here is basically the greater stiffness of silicon carbide nanomembranes. And in here, the sample was prepared on a 300 nanometers thick silicon carbide with significantly higher stiffness, or Young's modulus, than silicon, which was the previous material. And it was basically fabricated by etching the structure with focused ion beam, which I can discuss much later, but not now if anyone has questions about it. Yeah, the basic structure of the metamaterials is that it's about 600 by 600 nanometers, which is again a lot smaller than the wavelength of light that it is expected to interact with. So the first thing you want to know is the optical property of the material, right? And as you can see, yeah, when we took the transmission, reflection, and absorption signal of light incident on the material, there are distinct regions of resonances that are interesting, which I'll be discussing much later. But first, I'd like to talk a bit about the technique that I use to investigate these materials, which is pump probe transmission and reflection spectroscopy. And to understand how this works, maybe it's useful to get an idea of time scales of natural phenomena and how that works. So looking from the half-life of carbon-14, which takes about 5,000 years or so, this occurs within the scale of seconds, and then as you go, you start to see that at some point you're beginning to deal with really fast things, say beyond your camera, and then at certain regions, say in the nanosecond scale, things start to take a very optical turn, right? You start to see that a lot of the things are dependent on light. So for example, excitonic decay, which is basically how a lot of your semiconductors emit light. And this is where the usefulness of my of an ultra-fast laser comes in, which has pulses that are so small, occur within a couple of femtoseconds. And the technology itself might be new, but the idea behind it is as old as as Aesop's fables itself. So when you use ultra fast devices like a laser to investigate properties of materials, you're not really leveraging the speed of light because you can't really control that, right? If you did that, you'd be changing the properties of your material. So instead, we're leveraging quantities. And in the old fable of the rabbit and the hare, the tortoise and the hare, rather, what you've heard is that the hare got tired and rested, and that was it. But in the version that I heard, the tortoise was a bit more clever in that he got his family to line up at different sections of the route, so that no matter how fast the hare ran, there was always one member that the hare couldn't distinguish from the original tortoise, and they won the race. So the pump probe technique works the same way. And how it might work is that, so if you picture someone, say Ojuego, who's very talented, a very talented bowler who plays cricket, right, and can consistently throw balls at about 100 kilometers per hour. And on the other hand, you have another person, Temidire, she's a cricket enthusiast, and she likes to take pictures of the cricket balls to see how fast they're spinning. Temidire basically has two options on how to do this. She could go with the hare's wisdom and run 100 kilometers per hour while taking the pictures, or she could choose the tortoise's wisdom and leverage Ojuego's consistency by asking her to bowl several times and take pictures at different positions, right? And unfortunately, Temidire can't clock 100 kilometers per hour while she's running, so she chooses the tortoise's wisdom. So it might work like this. She says, okay, throw the ball, and then takes a picture, and then she asks her to move forward and throws the ball again and takes a picture. By the time she's done this several times, she gets an idea of how the ball is spinning, and then she can just basically relate that with time and know that Ojuego can spin balls at 5,000 rotations per minute or something. So the same idea is applied when you ground it to my experimental setup. So when you take the probe pulses, the pump pulses, for example, and they're incident on the sample at a very specific frequency, and then the probe pulses as well coming at a different frequency. Now that's Temidire taking the pictures, right? And then you have the pump, which is Odrigo, whose delay you can control. And then after every time the pump delay is moved, Temidire takes the picture. Now my laser might not be as talented as Odrigo and Temidire, but it can do something they can't do. It can pretend to be both of them by splitting the beam essentially, and then whatever signal you get, you interpret it. So yeah, going back to my material now, basically this was the optical property figure that you saw initially, and it's a simulated property of the metamaterial, and it is meant to just show us how light is absorbed at different frequencies or wavelengths, if you like, of electromagnetic waves. And as you can see, there's a very particular wavelength here where light is absorbed by the nano cantilever of my material. Now that is the wavelength that I'm interested in. And just to confirm, we experimentally took the optical properties as well and found and basically determined that there would be a range of pumping or applying Odrigo and a range of applying Temidire, which is taking the picture. And so that range is somewhere between 1050 and 1100 nanometers. And also because I've got a delay stage, I can extend the time range at which I'm taking these pictures from 0 to 3 nanoseconds, and then probe or take the pictures at around 800 nanometers and simultaneously collect it reflectively and from transmission signals. So the first thing that jumps out at you when you take that signal is that you'd observe two distinct characteristics, right? That's coming from your material. First is the pump-induced electronic effect, which I guess a lot of quantum physicists would find very interesting, but for me, it really isn't. And I can hear their collective gasps, but what I do, the second one is the optomechanical response, which is this really low signal that's highlighted here. And what I do is that I just chuck out the electronic response because it's not that important. And then you can see this really beautiful optomechanical response of my signal. And it's not so useful to look at it in time. It's interesting, but it's a bit like saying I go to the gym on Thursdays, the 13th, and Thursdays, the 20th, and Thursday. Like, that's not a useful way to describe how you go to the gym. You'd rather say, oh, I go every Thursday. And so I like to represent the data in the frequency domain. It's the same thing. So it's just showing me which of the signals are more prominent, and then you can see the main modes, mechanical modes on my structure, which were excited optically. And just to understand where all of these modes are coming from, I used a bit of simulation trick with a software called COMSOL. It's really cool, but basically it gives you an idea of how the vibrations are happening. And you can see that the main mode is the mode that the mode at 2.3 gigahertz, and then there's several other modes that reflected as well. I have superimposed the simulation frequency response, which is the black line, on the experimental response, which is the red line, the red curve that you can see. And so while there are some consistencies, not everything was represented, because I did just a single metamaterial simulation, and then I decided to also create some sort of simulation array which would be significantly slower, just to see where if there were other signals that I weren't accounted for in the single structure. So what I then found was that this very prominent mode at 5.3 gigahertz is a mode that's coming from the walls or the support structure, which you'd normally not see if you just you know, simulated a single metamolecular meta-atom. Like, another interesting thing that I did was that I then separated the directional force components to tell you which of the forces acting stronger. And this is important because in the optical simulation, we're able to separate the forces of the direction of the forces. And what we found was that the main mode was mainly, it's behaved in a way that is consistent with the Z optical force, which is quite interesting, because when you look here as well, the Z displacement is the most prominent displacement for the main mode. And this was also the same for the mode at 11 gigahertz, which is somewhere around here. And then on the other hand, the other modes like the 5.3 gigahertz was seemed to be responding to the Y directional force. Unfortunately, I couldn't probe lower than 1050 because of the limitation of the experimental. So I couldn't see that further. But anyway, it still does make sense, because if you think about a lateral force that's coming upwards and pushing the bottom of the support structure, the displacement would only be in Z and X of the support structure. You wouldn't really notice it in the Y direction. Another thing I thought was interesting to show was
sorry, just to jump in, Idris. So I want to make sure that we have a little bit of time. So if we can clip along, that'd be great. Thank you.
Yeah, okay. I'm done anyway. Other thing I thought would be interesting to show was just the general inhomogeneities that were on the structure because of the very the way that it was fabricated. So we noticed that on by taking on the signal on different parts of the surface, that, you know, there were wild variations in the intensity and the frequency. So in summary, basically we have seen an overview of metamaterials and their some applications. We've discussed the pump probe technique as a way to probe them, and also demonstrated gigahertz optomechanical responses for silicon carbide based metasurface arrays. Thank you very much.
Thank you so much, Idris. That was really interesting. And I've got to admit, so my last postdoc was on silicon carbide, but I was looking at the hardness properties of it rather than the optical properties. So it's really interesting to see about a completely different thing that I hadn't thought about. Also, really nice use of the Tiger logo for demonstrating refractive index and stuff. So we do have a couple of questions, and so what we'll try and do, we'll try not to spend too much time on this, but I still want to ask these questions from the audience. So Scary Boots asked, what made you want to study this research area?
That's a good question. So what made me really want to study is because I like really fast phenomena, and I do enjoy working with ultra-fast systems to sort of probe the tiny little responses that would, under normal circumstances, skip our eyes, you know, on a day-to-day basis. So I just really love fast optical phenomena. That's it.
I think that's as good a reason as you could possibly hope for, and I hope everyone in science has that same sort of enthusiasm. So one of the other questions that we have, this is from Rachel Oliver. So Rachel asks, are negative refractive index materials the ones you can use to make invisibility cloaks?
That's a very good question. I have an invisibility joke to tell, but there is nothing to see here. And, well, yes, I guess. And But also, I think what's more important, you know, than having negative refractive index as far as invisibility is concerned, is to have some sort of variable refractive index, so that when the light encounters any surface, the refractive index changes as it kind of moves along the surface, and so you can effectively change or warp the space that the light is experiencing. So yeah, I think it's more about the variability of the refractive index on some sort of metamaterial configuration than the refractive index. Yeah.
Fantastic. So I'm actually just going to ask one last question, if that's okay. So,
of course.
And of course, loads more questions are coming in. So there are plenty of interest, but I'll just ask one last. Do you do finite element modeling to predict the mechanical frequencies and properties?
Yes.
And how closely can this predict the real performance of the chip, real chip performance? And this is from layer lasers.
So could you repeat the last bit?
Sorry, yes. So
yeah.
How closely can the finite element modeling predict the real chip performance?
Right. So that's a good question. But I think, you know, they can give you indications of what sort of vibrations or oscillations to expect, but you perhaps won't be able to get exactly the intermodal relationship, if you like. And this is because it's not so easy to predict inhomogeneities on your material, especially when you're talking about really, really tiny structures. They're so small that any small inhomogeneity can create, you know, a massive change. And it's something that it's not so easy to model with, you know, finite element modeling. So yeah, that's it.
Brilliant. Well, thank you so much. Once again, thank you so much for your talk. It was really interesting, and I could actually talk to you about the production of silicon carbide later on as well, because that's an interest of mine. So thank you so much for your talk. That was brilliant. Thank you. The audience
thank you so much. I appreciate
reacting really nicely. So if I can ask if you can unshare your screen, and
yes.
Superb, thank you so much. Now I would like to introduce Dr. Kate Oliver. So the title of the seminar is "I Don't Think You're Ready for This Jelly, 3D Printed Shape-Changing Hydrogels." Making me hungry now. So Kate carried out their undergraduate at UCL in physics and published in semiconductor physics, and also worked in organic LEDs before they were cool. They then worked in science communication for 6 years, including time at the European Synchrotron Radiation Facility, the ESRF, in Grenoble, France. Then the Institute of Maths, and also at UCL Engineering. After seeing the fun of academia, they went to study at the Bristol Centre for Functional Nanomaterials in 2014 under the tiger Dr. Anela Snedden, who was apparently the best supervisor, and this is highlighted. Kate graduated in 2019 and started working as a science consultant at Innova Technology, where they used their soft matter nanoscience skills to help the R&D departments of big companies working on projects from snack foods to surgery. Kate also has a sideline in stand-up comedy and has rendered their PhD as an hour-long comedy special, which is not touring this year for obvious reasons. So with that, Kate, I'd like to invite you to share your screen.
Here we go, 3D printed shape-changing hydrogels funded by the Bristol Centre for Functional Nanomaterials. If you want to talk to me about this, this is how you get hold of me, and this is work done at the University of Bristol. Now, I very much appreciate everybody's patience in coming to see a talk about shape-changing 3D printed hydrogels and not asking the question, why on earth would you want to do such a thing? But in order to get that elephant out of the room straight away, I'm going to address it. And the answer of why I spent 4 years printing jelly is because pine cones. So pine cones are amazing. They are made of cellulose. They open when the weather is dry in order to disperse their seeds. They close when the weather is wet to stop the seeds rotting. They know how to do this without any sensors. They are completely integrated. They don't require any external power. They're not on the internet. They're not vulnerable to Russian or Chinese hackers. Not saying that there are necessarily any hackers from those countries. Pine cones can be buried underground for millions of years, and when they're dug out of coal seams, they still keep moving. This is pretty amazing, and this is the sort of technology that I would like just a little bit of for our human-built world. So that was the starting point. Can you build materials that are responsive and will have some of these amazing capabilities? So here's a sketch of what you might have if you've got a world where you can have these responsive shape-changing materials. Some of these shape changes might look eerily familiar from Dr. Ajia's pictures. So these are, of course, conceptual. I have not built any of these things, but you can imagine you might have a material that, when it heats up, would expand and when it heats up, would contract and cause a blind to automatically roll up when the weather is hot, or automatically roll down when the sun's shining on it. You could imagine objects that are that can have, I didn't mean to do that, you can imagine objects that can have two potential forms, because I can't be the only one who's got far too much stuff, right? It would be nice to have fewer things. Then you could have automatically responding things. So I'm finding it a bit of a pain to go out and water all my flowers. You could have a valve that automatically opens when the weather is too hot and dispenses water. Or you could have things that change once they're in the place where they need to be deployed. If you've got a medical implant, you could insert it into the body, and when it gets into that area, it would then open up and be the shape it needs to be, so less trauma for implantation. And if you see this big guy here, this is my idea of a soft robot butler that would bring you cakes. So there are plenty of things that I would like from shape-changing technology. And just to completely ruin any sense of suspense, I would now like to show you what I have contributed to shape-changing soft matter technology. I did some work to make it open source and more accessible. So here's the work of an example with things that you can print with the 3D printer that I developed. So I built my own 3D printer. I'm going to talk a little bit about that. Top is like a computer diagram of the logo of Bristol University. Should note here that this commemorates the founders of Bristol University, who made a lot of money selling tobacco, which was made by the labor of enslaved people, which isn't cool. Yeah, that's a bit of a heavy material, sorry. I shall now just leave that there and then move on to talking about the jelly. So I can show that I can print a complicated logo, such as that. What else can I also print? Well, I can 3D print some shapes, and then this jelly needs to be set by curing it with UV. So this is an example of the print head moving across some jelly that's already been printed, and this is to give you an idea of what the 3D printer looks like. So you will note it has a charming home-built quality. You will note it is located in a fridge. This is my affordable approach to cooling. And you will note that it gets squished out through a syringe pump, and that it's all got quite a home-built quality. And this is what I like to think of as bringing the accessible aspect to 3D printing, because this is a very cheap thing to build, and it brings this technology within the realms of a lot of different research groups and people. Then what does it do once it's printed? So this is an example of a shaped cured hydrogel, sort of a flat starfish shape, about couple of centimeters long, and when it's in water at ambient temperature, so around 20 degrees, it's quite large and flat, slightly splayed back perhaps. Then when you heat it up, it folds inwards and forms kind of a gripper type shape. So imagine that flower with the petals curling up and rolling in, and it also gets noticeably smaller. And if you'd like to see that happen in real time, you may now witness what an awful videographer I am. My apologies for the fact that my filming skills are not amazing. In my defense, I was very tired when filming this at the end of a long day in the lab. I have a very thin, sorry, I got confused at this point and filmed the background. I have a very thin printed jelly, and I'm inserting it into a container of hot water, and this is all in real time. Because it's so thin, the hot water travels into it very quickly, much more quickly than it would through a thicker material, and so you can see this folding up behavior. And what I've built into it through the way it was printed and the way the UV light created the jelly, it is what gives it this folding up kind of property. So again, we've got a thin flower shape, but this time it's folding up kind of on a time scale of seconds. Also, for those who aren't able to see the video, it's a little bit shaky because I'm not doing the best job of holding it still while filming with the other hand. I'm hoping this is endearingly accessible rather than amateurish. So having showed you where I got to, let's talk about how we did it, because we're here because we like little details. So this material was out there, 3D printing things that change shape. But what I did was think, okay, I'm going to do this with a material that other people can use too. And I'm going to shape it in a way that other people can access. I'm also going to work on modifying that material and seeing how else I can make it change. And finding a new way to get more behavior out of these materials. And perhaps I'm just not as good a scientist as Dr. Ajia. I think that's probably quite likely, that I made some mistakes while working on this, and a lot of my research didn't work out. And one of the things that made me saddest during my research was when things didn't work out. So I wanted to talk a little bit here about some ideas I had that didn't work, just so you can all get some perspective of failure. It happens to all of us. This is the work of other people. Beautiful. So the one on the left is printed with a Stratasys printer, and this blends plastics together. You've got a plastic that goes soft at one temperature, a plastic that goes soft at another temperature. Blend them together, get plastics that go soft at temperatures in between, and you can make things that fold up in order. Beautiful, lovely work. And on the right hand side, you've got an example of self-folding jelly. So this is work out of the Weiss Institute at Harvard. And again, it's printed with a lovely, detailed, but incredibly expensive printing system. So you're looking at significant fractions of $1 million to print out these things. And that's what I mean when I say this isn't accessible to everybody. Obviously, a lot of technologies are very expensive at the start, but also obviously repeatability helps make better science. This is my attempt. Let's take that and make it affordable. Let's affordable material, affordable printer. So this is my affordable printer. This is my affordable material. Oh, apparently I cannot play the GIF. Well, it's a material called polyisopropyl acrylamide, which has an interesting property that when it gets over a temperature of about 30, the polymers would rather contract in on themselves than be in contact with water. Under 30, it's very happy to be in contact with water, which is why you can make it into a gel structure. And when I'm talking about gels, I mean generally any structure that's sort of like a network of long, thin molecules with a liquid in the middle. And here that liquid's water. And in this example, the molecules would be isopropyl acrylamide. And then when those get hot, as I say, instead of having lots of water in the gaps, they don't want to be in contact with any of that nasty water. So they scrunch up and thus make the whole material overall a lot smaller. That's cool. It's got a really good thermal response. So we've got part of the solution, but it's incredibly brittle. I don't know if anybody has tried doing mechanical tests on basically contact lenses, but it's very difficult. So I blended it with another material. And this is alginate, so it's extracted from seaweed. And if anybody's had, anybody is like me quite cheap, and you have had those little olives that have in the middle of them the red bit, that's often blended with alginate because cutting off a whole piece of pepper is very difficult. Then you'll have eaten alginate. It's used as a supplement in many things. It's very, very benign and available in loads of places across the planet. And alginate is interesting because it's bound together electrostatically. So the polymers are negatively charged, and then you join them together not by making them into a network with chemicals, but by physical responses. You have two negative things and you sandwich a positive thing between them, and that makes joins between the polymers, which allows you to again get that kind of network structure. So together you've got two networks going on, one made of alginates, which is held together by electric charges, and one made of NiPAM, which is held together by chemistry. And they each bring something to the table, one strength, one thermal response. It makes quite a thick mixture. I don't know if anybody's been, I would hope people have been using hand gel at the moment. It's that sort of texture. So if you imagine trying to print that and push that through a syringe, it's quite an ask. But if you imagine printing with this, yes, it's thermoresponsive, but if you print something that's just responds the same way to temperature all over, you've made the world's most boring print, right? Something that just shrinks perfectly in proportion as it gets cooler. So ideally, we'd like to be able to have a couple of materials, something that shrinks more on the top and less on the bottom, so it bends, something like that. Had an idea to do it. When you're working in a center based on nanoparticles, the answer is pretty much always nanoparticles. And the concept here was you can use nanoparticles to convert light into heat if the light the wavelength of the light is particularly aligned with the size of the nanoparticles, so they're in resonance. Another connection to the last speaker, no planning. So could you put nanoparticles into a hydrogel, hit them with a laser, and have a light activated 3D printed thing? The answer is yes, probably, but you would need an incredibly powerful laser and more nanoparticles than I could afford, so I would need to make my own nanoparticles, and I am not the world's best chemist, I have to say, hold my hands up to this. We had a go, it was great fun. Anybody wants to ask me, have I ever fired lasers at a jelly? The answer is yes. I'd like to say thank you to Dr. Tom Oliver for helping me try. No relation to myself or Rachel, there's just a lot of Olivers in science. So that was an idea that didn't work. This is the 3D printer I built. If anybody's interested in the details of this, I'm pretty proud of making it, which is why I include it, even though a lot of people aren't interested in the details of equipment. But basically, I took an off-the-shelf 3D printer, an open source design for a syringe pump, thank you to Michigan Open Source Technology project there, added some microfluidics elements, commissioned a LED PCB from Shenzhen, and added a power source, wired it into the 3D printer. So after all my modifications, it was able to print like it would have done beforehand with plastic, but instead of printing out plastic in a heated element, it squeezes out a line of this jelly, which kind of has a texture like hand gel, and then zaps it with UV so it goes solid. And one of the things I did was integrate that UV light on it so that the UV light is controlled by the same instructions that you send to the printer to tell it where to go. So at the same time you say, you know, kind of move around here, draw a line this long, stop, then pull up, you can say, make it this hot. Make it, hit it with this much light, and that would make it this solid, hopefully. So I'll hold my hands up. It's not my concept to print NiPAM alginate. I read it and thought it would be good to use it. I built on the work of others. What's new is my integration with it in an open source documented system, working on the documentation now, and integrating it into the print process so you can do it all at once. And I found a really interesting effect. This is the never seen before bit, and that's why we've got these warnings about please not sharing it around, because I'd like to get this published ideally. This is a cool effect. If you hit the sample with UV light and then you put it in cold water, it bends a little bit away from the direction you hit it with light, and then when you heat it up, it bends up a little bit towards. And people say things like, oh, well, maybe that's due to, you know, evaporative effects at the surface. And that's a really good point. But my supervisor, who is the best, Dr. Seddon, other supervisor, Professor Ical, also very good. But this was Dr. Seddon's idea. You just do the null. You set everything up exactly the same and then hit it with light from the bottom. And then it does the exact opposite, which really neatly illustrates that, no, it's probably something to do with the light effect, isn't it? So this is awesome. This is how I got those effects that I showed you at the start, and they're tailorable depending on how thick the gel is, which again sort of suggests it's the UV doing it. But the process of polymerization is quite complicated, and it's also quite sensitive. You know, these would be different depending on if it was a humid day outside or what temperature was going on. So it's quite a difficult process to control. If I was selling this in a paper, I would describe it as tailorable. You can also use it to get interesting directional effects. So you can see here the difference between a bar that bends up in one plane, forming kind of a section of a ellipse, to a bar that forms a helix, depending on the direction of the illumination. But it was really hard to get these reproducible, and this is where, again, I'd like to acknowledge my limitations. I had a really hard time reproducing these results. And part of that is because I didn't really know what was going on. I didn't know what was important to control, and I still don't. I did a lot of testing to try and find it out, though. Take you through that briefly. So far, this has tried to be very accessible. I'm going to go into a little bit more detail there. So you can also change shape in 2D shapes. And interestingly, you can change the Gaussian curvature of the surface. So for maths nerds, that's a fun fact. And here's my beautiful flower that I'm very proud of. Why is it good? It's another way to change 3D prints. So 3D printers are kind of appealing because you can make any shape you want with them. If the shapes that you make can then change, that adds a whole new degree of options. It's integrated into the printing system. It's quick. It takes about 30 minutes. It gives you a gradient, and gradients are interesting rather than binaries, and, you know, insert gender comment here, but it's if you can get a whole gradated performance, it's ultimately more efficient than having to combine two binary effects. There's detail on that I can go into elsewhere. If you wanted to do this another way, it's very complicated. This is by far the easiest way that I've read of to get this effect. And if you see what we sort of hinted at with the 2D, you can get much more complicated behavior. But I keep coming back to this, it's not incredibly reproducible, and it'd be really nice to know what's going on. So the origin of asymmetry, yeah, Muse fans, out of date. It's clearly something coming from the light, and it's clearly some difference in the gel that causes a gradient. So what's going on? One obvious thing was evaporation. We kind of eliminated that. One is chemical differences. So maybe there's some difference in the composition between the top and the bottom. Maybe there's some change in kind of, you know, I spoke about the mesh of that gel. Maybe in some places the holes in the gel are really small, and in some places they're quite big. Or maybe, you know, the network is somehow structured differently. Maybe at the top, you know, the gels are really well connected, and at the bottom they're quite loose. Maybe like at a meta level, you know, there's like channels through that network. Maybe there's big holes in the net. Or maybe there are more things in heaven and earth than they're dreamt of in our philosophy. Quick check for chemistry. Don't propose to explain Raman spectroscopy unless anybody would like it, but suffice it to say this is a way of checking what bonds are in the material. And I did a lot of measuring, and it suggests that the 1 part in a million, the top and the bottom of the sample were very much the same. And thank you to Andre, Anna and Chris, who helped me a lot with taking these measurements. I tried confocal laser scanning, which was the best way to image these gels I found. I would not recommend other methods of scanning gels. Can talk about that if people are interested. But I couldn't see much of a difference. On the other hand, these gels are very irregular structures, and if you're sampling an irregular thing, you need to sample it lots and lots of times in order to draw a reliable representative statistical correlation. So I think this probably is the best way to find out what's going on. And many thanks to my friend Yatsin Rios de Landa for helping me take these measurements, which were the best insight I had onto the phenomenon. And why I have a lot of sympathy for other people doing work with gels and microscopy. So I'm afraid I've come up with a blank, which is why this is not published yet, because I was having trouble figuring out how to put it together, because in science we like to tell a neat story, and sometimes life just doesn't tie up neatly. I think what's probably going on is that there's some difference in porosity between the top and the bottom, but it's quite subtle, and you'd need large amounts of scanning in order to get an insight into what's going on. But I'm open to suggestions, and the phenomenon definitely exists. It definitely is interesting. It definitely is tunable. And I think it's something other people could potentially build upon to get more kind of soft shape-changing devices. I'm going to put this up just because I wanted people to have access to ways to contact me and ask more questions. I am present on Twitter, I have a website, I do videos of my stand-up, and I will try and answer email if you write to me. I say try because sometimes I get a bit overwhelmed and tired, but I will try and get back to you, and if I ignore you, it's not personal. Please just remind me. It takes a village to raise a child. It takes a university to raise a thesis +1. Many thanks to my supervisors, my mum and partner who scraped me off the floor when I was dealing with a lot of depression, and PhDs really put you through the ringer, and my fellow students and the staff of the School of Physics who really helped me a lot, and my fellow science performers. So if you're intrigued by the idea of stand-up comedy about science and extremely technical things, I recommend looking up Science Show Off and Side by Southwest. And also, if anybody in the chat is a UK taxpayer, thank you to you, because I funded my living through an Engineering and Physical Sciences Research Council grant through my PhD, and that was funded by the money that you pay that goes to the Research Council, who decided that I was an appropriate candidate for this, and I'm very grateful for that. So conclusions, if you want thermosensitive cheap hydrogels, nipalmarginates, I would recommend. You can build an open source 3D gel printer for much less than half the setup, but you're gonna have to fuss over it a lot, and it might just sometimes break some days, sorry. There's a really cool gradient effect that pops up sometimes, but where does it come from, and how can it be made repeatable? And can I entice somebody to either publish this or continue my research and make it into something better? I'm not sure, work in progress. Well, thank you everybody for listening, and oh, sorry, I didn't intend to show you that one, bit of a spoiler. Thank you everybody for your time, and I'm going to take a few questions now, assuming we've got the timing for it.
That's awesome, thank you so much, Kate. No, that's great. I wonder whether you want to go back a slide so that people have your contact information while we're answering these questions. Possibly, you might not want to, but
no, I think that was a great idea, Clara. I experimented with a non-traditional arrangement, and I'm not sure I'm up with it.
No, it works. I like it, but it's nice to have this up while we're here. So there are a number of questions. There's some great comments, and we have got time to answer a few. So one thing, and I think you sort of went into this, but one question that we had from KS was that 3D printing looks great for shape control, but are there limitations to the technology? So obviously we talked limitations, but is there anything that you sort of highlight in that regard?
Oh gosh, well, I have a whole chapter about this. I would say the major limitation of 3D printing is that it's slow. So you're covering every bit that you want to print. You have to go over it. So if you want to print 5 things, it's no quicker than printing 1 thing. So there's no economies of scale, which is really annoying if you want to do something multiple times. And just with regard to jelly, I mean, it's a bit awkward making everything out of jelly, I'm not going to lie.
I mean, I trouble just making jelly into traditional jelly shapes, so yeah, I can understand that. What you're doing is far more complex. We have a question from Izzy. Do you have to pre-program extrusion speeds when you are printing composite structures?
I probably would have to if I'd ever printed a composite structure. But no, this is what I particularly loved about this material is that you print all the same material and then you bake in the difference in response by doing different UV exposures, which gets you away from that really awkward bit of trying to print it all out at the right speed. And of course, there's the fun aspect that this liquid happens to have a property called shear thinning, so that as you squeeze it and start pushing it out, it becomes easier to squeeze. So you can imagine that when the material you're trying to squeeze is changing its response to squeezing, that's going to be an entertaining thing to try and control.
That sounds great. Becky Nisbet asked a question, and I think this is interesting. How would it work to get a medical implant to open at a certain organ or location in the body? So I guess this is about how we can control when it opens, especially if we don't necessarily, can't necessarily see it directly. And I guess that's quite complicated.
Well, I have off the top of my head 3 ways you could do it. One is hydrogels can be responsible to a number of things, not just heat. They can be responsive to pH. I understand, and I'm not a medic, so don't inject jelly onto yourself based on anything I say. But I understand that tumorous environments often have a different pH to healthy tissue. So, for example, that could be relevant. If you wanted to go to a particular organ, and I knew somebody who was working on swallowable devices that would activate once they hit the acid in your stomach. So in a healthy person, that could be an option. One option is that, and this has been done in animal models, is that if you have nanoparticles, you can trigger them using infrared. Human bodies and animal bodies are generally transparent to infrared. So you let them go in, you zap them with a laser, and inside you trigger those nanoparticles, and that makes the response happen. And the other option, which is super awesome, is you can have little custom bits of DNA, and they act like little bits of Velcro holding the hydrogels together. And they pair okay with their own partners. But if they meet a bit of DNA that is like a super amazing fit for them, they're really fickle and they'll just sod off and be like, no, you're the best DNA for me. So what you do is you tune it so it kind of matches with only the sort of DNA or RNA, and again, I'm not a biologist, that it will meet in the environment you want to see. And then you send it in, and when it gets to that point, it just goes boop, and the half of the connections break up. So those are things that I think I put a reference to in my review paper of 2016, but possibly they have happened since. But definitely those are available, and I love the crazy things people do with jelly. Sorry, ableist language. Oops. Sorry, I meant I love the wild things people do with jelly, and I apologize.
Yeah. Thank you. Yeah, so there's a couple more questions coming in, but I am conscious of time. Although there is someone that's also working on PNI, PAM, hydrogels.
NIPAM to its friends.
Yeah, so that's a first year PhD. And so this is AIF, and they asked, how do you know there is no cross-linking gradient or separation and alginate? Oh, between the material and the alginate.
Oh, cross-linking gradient. So if there was a cross-linking gradient, cross-links would be indicated by the presence of a different kind of bond. So the Raman spectroscopy would pick up the presence of different kinds of bonds at a different density on different sides. And there are different bonds in NIPAM and alginate. So again, on the other side, one would expect to see more of the sort of bonds that are characteristic of NIPAM on one side and more of the kind of bonds that are characteristic of alginate on the other. And their ratios don't change to, as I say, 1 part in a million. So that's what I base that on.
No, that's fantastic. And I'm going to ask you one last sort of technical side on the printing, technical question on the printing side. But Amy Roberts asked, do you use slicer software or Xcode for the potentially more complex shapes? So I guess this is how you program the printer.
So I use Slicer. Slicer is my favorite. I have custom settings for it, but I also wrote a really inefficient compiler, which takes in G code, strips out the bits of it that aren't relevant to me, and then reprocesses it for UV, because I was too lazy to write something that would track my own head movements, but wanted to mirror them for a second, like that was for kind of like squeeze it all out, then go back over it once or twice with a UV light, but only in the areas you're interested in, that sort of applications. Yeah, I'm a very beginner coder. I acknowledge my my failures. Gosh, would you not employ me as a coder?
I don't think it's acknowledging failures. It's acknowledging our skills, because we're all good at different things and no one can be good at everything, right? So I see that as acknowledging our skills.
True. Well, in which case that is an area where I have a lot to learn, and I'm delighted to meet people who have more experience than me. Also, I'll try and stick around to answer questions in YouTube or on Twitter if people have more, and they can always email me if that would be an alternative.
Fantastic. Well, thank you so much. With that, I'll ask if you, I'll invite you to stop sharing your screen, and thank you so much for another interesting talk. Both Idris and Kate, thank you so much for your talks. They were both really interesting, and I think there was a lot to learn, and looking, hearing about the questions, it sounds like conversations could go on for days. So hopefully, like I say, do follow the Kate and Idris on Twitter and the various links that they provided. So with that, I'm going to close the talk. So like I say, thank you once again to our speakers, and also thank you to our wonderful audience for asking questions and being respectful during this conversation. It's fantastic. I'd also like to remind people that we are, in memory of the physicist Claudia Alexander, we are asking if people are able to look to donate to Generating Genius, which is a London-based charity helping school students from disadvantaged backgrounds, particularly Black and BME, to enter university and enterprise careers in STEM. So that's a really great charity, and if you're able to, that'd be really great if you can support them. I believe there should be links in the YouTube chat or the comment or the description. I'd also like to thank very much the team of Tigers for helping to do this. There's an awful lot of work that goes into this, and so it's really great. I'd like to thank all our members, Caroline, Clara, Catherine, Izzy. I feel like I've forgotten someone. It seems that most of us have names that begin with C or K. But with that, thank you so much. Thanks everyone for joining us. We do have an event next week. So we have another couple of fantastic speakers. We've got Claire Malone and Cheyenne Paulus. And so I'm really excited to hear this. This is on particle and astrophysics, so less of my area of expertise, so more of a chance for me to learn, which is always great. And so we'd love to see you and have you join us next week for that, if you're able. And with that, thank you so much. And hopefully we'll see you next week. Thank you again to our speakers. Bye-bye.
Thanks. Just one, Kate, did you want to say one last thing before we log off?
I can't find the on button. No, I'm not muted. I just wanted to thank the speakers for organising. That was all.
Okay.
It was on my to-do list, and I wanted to say that I really hope that this sort of event becomes a vector for bringing together those of us who might not traditionally have been represented to support each other and build, get us ahead in our chosen field of endeavour in a collaborative way, showing that you don't need to be part of the old boys network to come up, and we can help each other to get ahead and enjoy each other's success.
Wonderfully said. Thank you so much. And on that note, we will end. So thank you so much for joining us. Thank you for our chair, Clara Baker, Dr. Clara Baker, for chairing the session, and we will see you next week. Bye.